Hello, we're going to take a look at a flexible string designed to have a fundamental frequency equal to that of the C4 note, namely 261.6 hertz. And we're going to pluck the flexible string at 1/9, 1/2, and 2/5 of its length and compare the spectral response. And then we're going to take another look at the 1/9 of its length string, and we're going to compare a stiff and a flexible string under those conditions. So we'll start out now with the string plucked at 1/9 of its length. Okay, here's the initial profile. It's been extended and it's plucked at 1/9 of its length. And I'm solving this equation using the closed form solution, which in turn requires a Fourier series approximation of this initial shape. And this is the way it looks. I'm using 54 harmonics in the approximation, and you can see, for example, that the 9th, the 18th, 27th, 36th, and so forth, 45th, 54th are 0. And I'm mentioning this because one way to look at the response of a string is that the initial position can be approximated by these various sine waves with these various coefficients. And you could take each sine wave by itself and send that as the initial position, and then look at the response to that one particular sine wave. And then at the end you could add them all up, and that'll give you the solution to this shape we see right here. The reason I mention this is because, for example, we would then expect the spectral response of the final result not to have anything at these multiples of 9 harmonics, because there's no input at those harmonics. Okay, let's see what happens here when we start the simulation. Okay, here the peak is propagating to the right. It's going to be reflected and inverted, come back. Notice how it turns the corner there. Watch how it's going to stop. It goes up and then stops. Okay. You can see that, for example, in theory, the line should be totally straight across here, but there's a few kinks in it because of the fact I'm using an approximation to the initial position. I'm only using 54 harmonics in that approximation. Okay, let's take a look at the force at the right-hand side of the string, which would be where the bridge is located. And you can see here's a plot of the force for this one cycle, which takes 3.82 milliseconds, which is the period of the 261.6 hertz signal. So we start out, the slope is around at least 0.9 on these force units anyway, which is associated with this slope over here, because the force on the bridge is going to be proportional to the slope of the flexible string. And the string right now, at the end of that first cycle, is pulling up. So when the slope is negative, which it is here, the force will be positive and it'll pull up on the bridge. And so at the very end, which is right over here, 3.82 milliseconds, the force is about 0.9. However, when it goes and reflects, as you might remember when you saw the picture, the slope is much higher and it's positive when it reflects and inverts. And so it goes down to -7 from 0.9. But it doesn't stay there long because it doesn't spend much time in that inverted position. Let's take a look at the whole cycle snapshots of the whole cycle. Okay, here's the picture again. We start out, here's our initial position when we start to pluck. We release the pluck, and we start to see this peak start to move towards the right hand side where the bridge is located. Comes over here, it is reflected and inverted. Now you notice the slope over here is not high. It's negative and it's pulling up on the bridge. Now right here, for example, the slope is rather high, at least magnitude-wise. It's negative, but it's magnitude-wise it's high, and it's pulling down on the bridge. And then it gets inverted and reflected and starts to come back in the direction. And now the slope is again negative and not very high. And that is consistent with that plot of the force for the cycle, lasting 3.82 milliseconds. Low slope, low force, high slope, high force. And this is going to repeat itself for the whole, as long as you want to run this string. So then for a longer run, I ran it for 20 periods. I collected the data, calculated the slope, and did the line spectrum of the force. And this is the result here. First 22 harmonics, up to almost 6,000 hertz. Here, for example, is the first harmonic at 261.6 hertz. It's the strongest. It comes off. The harmonic of the force, the ninth harmonic, is basically zero. It's 55 dB down from the strongest harmonic at 261 hertz. Also, the 18th is diminished, again, greatly compared to the others. Okay, that was the sound of the force, which would be the sound of the note, and that'll be compared with C4 on a regular piano, not a regular piano, but that's actually a Yamaha P120, but it sounds similar. All right, let's go take a look at something else here. Let's take a look at the string when we pluck at 1/2 of its length. Okay, here's the initial position with the pluck point right in the center of the string. The string is 51 centimeters long, so it's 25.5 and is the center point. Once again, we have to make this solution the way I chose to do it. You have to make an approximation of the initial position Fourier-wise, and here is the coefficients in the approximation. You can see all of the even harmonics are zero because this is a symmetric initial profile. So we're not going to see any strength at the even harmonics at the final result. Okay, let's start the simulation. It comes down. The two peaks spread to the left and the right, come down and repeats itself and gets inverted, comes back. And you might notice that the slopes over here the slope is negative, it's pulling up on the bridge. And it was down at the bottom here, it was positive and pulling down on the bridge, but the slope was the same. So the force will be the same in both directions. For example, up here the force is around 6.5 force units, and when it gets reflected and inverted and is pulling down on the bridge, it's minus 6.5 force units. Here's the overall picture of the one cycle. See, it spends a lot more time pulling down on the bridge. In fact, it's an even amount of time as it is pulling up on the bridge. And you can see it consistent with the force plot. All right. Here's the line spectrum of the force on the bridge. Notice that all of the even harmonics are about 50 dB down relative to the dominant harmonic at 261.6 hertz. And there's the sound of that particular choice, and here's the C4 on the Yamaha P120. All right, now we're going to finally do the thing for 2/5 of its length. See, here's the peak point right here, so it's a little bit off center. Here's the Fourier approximation to the initial position. You see the 5th, the 10th, the 15th, multiples of 5. Those harmonics are 0. Here comes the response, the two peaks moving left and right. Inversion, now we're pulling down on the bridge. Now we're pulling up on the bridge. Okay, that's one cycle. Here's the force. See, it's not quite symmetric because the slope, when it was inverted, was about -6.5 when it's in the positive plate, and when the slope is negative over here, pulling up, it's about 4.5. And the amount of time in those two positions is different because the pluck point was not in the center. Here's the three-dimensional picture of the snapshots of the cycle. Here's the force again. And here's the line spectrum of the force on the bridge. Again, we have our harmonic fundamental here, 261.6. And then you see the 5th is about 50-some dB down, as is the 10th, 15th, 20th, and so forth. Here's the sound. Note the beating. There's the C4 on the piano. Okay, now let's compare the three different plucks from the point of view of sound. Here's 1/9. 1/2. 2/5. Okay, we're going to continue now by comparing the flexible string with the stiff spring for the case where it's plucked at 1/9 of its length. And because of the more challenging problem for the stiff string, I chose to solve the differential equation, which is now 4th order instead of 2nd. I chose to solve it numerically, which means I'm not going to be using Fourier series. It also means that I should do the same thing for the flexible. So I'm solving the flexible string and the stiff string numerically. And the results are going to be different because we're going to have to deal now with round off here. Okay, let's start and see what happens here. Here is the initial position. I've got two strings plotted here. I've got the flexible in blue and the stiff in green. Okay, at 0.15 milliseconds, you can see the familiar initial position of the flexible in blue. Comes up, changes slope slightly, goes over here, and then comes down. Right away, you can see there's a difference in the stiff. It does not have as much sharp turns as the stiff. In other words, it comes up and turns the corner smoothly. It turns the corner down here a little bit differently. Here's a 0.3 milliseconds. Once again, you see the stiff is coming out and turning corners. Has a little undulation there. The flexible is coming up and turning the corner sharply, relatively speaking. Okay. One of the things you can see happening here is the stiff string is starting to lead the flexible. Okay, that's almost 10 milliseconds of simulation. let's take a look at one cycle for each case. Here's the flexible. You've seen a graph similar to this before. You can see it comes up, turns the corners relatively sharply, comes down here. You can see this. You can't really tell from this graph, but the slope is a lot higher magnitude-wise over here than it is over here. You can also see that the corners are being turned more smoothly. You can see a little bit of undulation up here. We're getting curves instead of sharp corner turns. Okay, now I collected the data for 20 periods and calculated the force. You can see they come over here and then they spend some time at this low position corresponding to pulling down on the string, so the force is negative. And then they go up, but you can see the difference between the flexible and the stiff. Flexible is in blue, stiff is in green. The flexible is making a lot wider variation. See, flexible in blue is going all the way down here, -12 in force units. The stiff is going down to -6. And it's a much different acting response. You can also see over here that it gets kind of erratic, which is probably related more to the numerical method involved rather than the actual physics going on. Anyway, that's the difference in the force, and it makes sense because the stiff string is not going to turn the corners as quickly because it's stiff. It has elasticity. Okay, here is the line spectrum of the force. You can see I've plotted the harmonics in red. So we start out, and the stiff and the flexible for 261, the first harmonic, are right on. And then over here there's a little bit of a deviation, but then by this term here, the third harmonic, you can see that the flexible is right on the red line, which is the harmonic, and this stiff has started to move to the right. Whoops, I don't want to do that. Go back. And then it gets more and more pronounced. When we get to the 9th harmonic, you see there's nothing there for the flexible. By that time, the 9th partial for the stiff has moved over here. Then the 10th harmonic is right on for the flexible. The 10th partial is diminished quite a bit. It's down almost 45 dB. And then it starts to pick up. But at these higher harmonics out here, the stiff is not anywhere as strongly represented because it's not turning those sharp corners. Okay, let's go there. And I'm thanking you for listening and watching, and I'm suggesting you take a look at some other videos on this website.